Hello. Uh, good afternoon.
Yes. Hi, Shutin. Hi.
Oh, hi.
Hi.
How about the slide I will control? Hi, everyone.
Shutin, for the slide, you can go to the bottom of the screen. There's a icon next to the video icon. It points it tells you share content. Can you see?
Yes. Will I share?
When your turn to speak later.
Okay.
Okay, yeah?
Yeah.
Thank you, Professor. Thank you, bro.
Mm.
Hello, everyone.
Hi, Prof. Ani.
Hi, Prof. Hi. Alexander, Prof. Putin,
Hi, Papani.
everyone. Yeah. Good afternoon.
Yeah. Professor. Also, Dr. Pamjit and also Dr. Avinesh, right? I just like to say hi. Are we supposed to turn on the camera throughout the session?
Yes.
Oh.
I mean, ni tak boleh apa? Dah okay. Can you all hear me?
Yep.
Okay, good.
Thank you.
Okay, good. Terima kasih, Syafiq, ya. Okay, so I think what we are going to, how we are going to do this is when the speaker, when it comes to the turn for the speaker to speak, then only you turn on your mic lah, or else maybe when the others are speaking, we can turn off our mic so that we will not make any, unnecessary noises as the background lah, when there are somebody speaking. So I think we should start now because it's already 2:31. Not able to hear anything. Can you all hear me?
Can you hear me? I'm Lee.
Oh, tak boleh dengar lah. Oh.
I can hear you very clear. I can hear Putin. I can hear Dr. Mimi.
Prof. Ani, can you hear me?
Can you hear me, Dr. Mimi?
Yeah, Chuti, Prof. Lee, I can hear you. I can also hear Professor Ani. What about Professor Avinesh and Professor Amjit? Are you guys here? Yeah. Okay, great. Okay, so you all can hear me, yeah? Okay, so I think I can start now. So Assalamualaikum warahmatullahi wabarakatuh, and a very good afternoon to all our honorary guests, distinguished speakers, and all participants and audiences from Malaysia, as well as those who are joining us today from outside Malaysia. So welcome to the virtual meeting session uh, this afternoon entitled Sustainable Food Waste Utilization and Management. So this meeting is organized by UTMShine under the Office of the Deputy Vice Chancellor, Research and Innovation, Technology Malaysia, or what we call here as the DNCPI Office, in collaboration with St. Longwell Institute of Engineering and Technology, or also known as SLEET, located in Longowal, Punjab in India. So today we feel very honored to have four prominent speakers, researchers in the field, to be the speaker for our session. Two from Malaysia, UTM, and which are Professor Andres and Professor Lee Chutin. And we have another two speakers from India, SILT, SLEET to be specific, Professor Pamjit Panesar and Professor Avinesh Thakur. And we also feel very fortunate today that the director of San Langawal Institute of Engineering and Technology, Professor Sailendra Kumar Jain, to be with us today. So thank you very much, sir, for making your time to be with us today. So without further ado, let us first open up our session today by welcoming Associate Professor Dr. Zainul Akmal Zakaria, representative from the DNCPI Office, UTM, to give a word or two as the opening remark. We are also very proud to share here that Dr. Zainul is currently the chairman of UTMShine. And UTMShine is an initiative initiated by the DNCPI office to encourage young researchers in UTM to pursue high impact research and producing high quality research output. So Dr. Zainul, please welcome.
Thank you very much, Mimi. That was really a kind introduction. I really feel very flattered. All right. My name is Zainul. I'm from School of Chemical and Energy Engineering, UTM. So as Mimi explained, we are actually a unit under the DVCRI office. So DVCRI itself, President Dr. Fauzi bin Ismail, and hope that we're going to have a very fruitful discussion and sharing session today. And he is looking forward to have more engagements, collaborations, leading to more collaborations with our institutions. And just echoing his statement, hopefully everybody will have a very nice sharing and discussion today. All right. So with that, I pass the session back to Mimi. Thank you very much.
Now, let us all welcome Professor Shailendra Kumar Jain, the director of SLEET, to also, give us a few words or to give us an inaugural address before we officially start our session today. So please welcome Professor Jain.
Thank you, Mimi. Good morning, all the guests, speakers, organizers, all the participants. It's my proud privilege to be at this particular inaugural program webinar on sustainable food waste utilization and management. It's a very relevant and timely topic. I would like to inform about our institution. The Sant Longowal Institute of Engineering and Technology is fully funded by Government of India. Our institute is mainly working on a pattern of modular education with multi-entry, multi-exit option. We offer admission after 10th standard to 3 years integrated certificate and diploma program, where our students are having exit option after 2 years with a certificate, or if they complete 3rd year, they will be awarded certificate. Then 50% of these students are admitted in 2nd year engineering program, whereas the 1st year engineering students are admitted through joint engineering entrance exam conducted at national level. At the same time, we are running master's program in 7 engineering discipline and 3 MSc program in physics, chemistry, and mathematics. And all 11 engineering department, including engineering sciences and humanities, they are running PhD program. So we have an entire range of students right from 10th pass out, 12th pass out, as well as entry with PG and PhD level. Our food engineering department is very rich in terms of the faculty experience, their publication quality, and 2 of our faculty, Professor P.S. Panesar and Professor Avinash Thakur, are basically as participating as expert in this particular webinar. So I would like to emphasize on the topic is the food processing industry is basically one of the largest industry in the world, especially in terms of production, consumption, and growth prospects. Whenever we talk about the mankind, the food is the first and foremost important requirement. Without food, none of us, neither a human nor any other creature on the world, can survive. Now, there are various sectors on food processing industries that are engaged in processing of various variety of agriculture commodity, fruits, vegetables, milk, poultry, cereals, pulses, oil seeds, and plantation products. Though food industrialization has generated a large quantity of food products, provided employment, that is the important. While talking about the food processing, it is generating the employment, of course, economic benefits to a large number of people. But at the same time, it is generating huge quantity of biodegradable waste. Not only it is the loss to the food, but also causing environmental pollution. Worldwide, food and agriculture industries produce annually large volume of waste and byproducts, which causes a serious disposal problem. How to dispose this waste? This is an issue. These waste, whether solid or liquid, on one hand are direct loss. If we can save this particular loss, that is addition to the production, but at the same time it also generate environmental pollution, which is basically a great concern for the entire world. The generation of waste is not only economic loss but also require additional cost for their management. Other way, we can also say that yes, of course, the food waste management again generates some employment in addition to the reduction in the loss. These waste can be considered valuable byproduct if we can manage them properly. If suitable techniques are used for their bioprocessing to increase their values. So here I'll see that there is an opportunity, there is a research potential that how we can basically utilize this waste as a byproduct. Recycling, processing, and eventual bio-utilization of food processing residues offer potential of these byproducts in production of value-added products. So I must say that the theme of today's webinar is very well thought and need of the hour. The webinar is focused on the sustainable food waste utilization and management. I believe that the deliberations made will definitely add value to the food industry in terms of how we can minimize this loss to the food, how we can utilize this waste and have a better management. Once again, I would like to congratulate the organizer. Thanks to all the coordinators and welcome to all the speakers. Thank you. Wish you all the best to all. Thank you for giving me this opportunity.
Thank you very much, Professor Jain. We cannot appreciate you more for introducing us to the wonderful SLEET Institute. And thank you very much also for the very nice introduction that you gave to our topic today. Thank you again, Professor Jain. So,
thank you. It's my pleasure.
Yeah. I believe all of you here can't wait to listen to our first speaker, Professor Lee Chu Tin. So basically, Professor Lee is a professor in solid waste and composting. Professor Lee did her PhD in University of Cambridge and Masters in University Technology Malaysia. So until 2019, she has an H index of 23 and produced papers with cumulative impact factors of more than 70. She is an associate editor for the Journal of Cleaner Production. And from the flip coin side, outside the academic world, Professor Lee is very active in doing CSR work related to solid waste composting and sustainability efforts involving schools and local communities. So this afternoon, Professor Lee will be talking on turning food waste to value-added products, challenges and opportunities. You have around 20 minutes, yeah, Professor Lee? And to all audiences, we will only open the question and answer session once all the 4 speakers are done. So meanwhile, you can jot down your question in the WebEx chat or FB, the Facebook live chatting medium. So without further ado, please welcome Professor Lee.
Thank you, Mimi, for your very kind introductions. Thank you so much for inviting me to come to these sessions. It is indeed my honor, and I am also very pleased to see the potential and future collaboration between UTM and SLEET. Because my topic is wider than the rest, therefore the chair lady has given me the first chance to speak. This is indeed my honor. As we all know, solid waste is a big problem worldwide. Despite we have talked about this problem for decades, there is still small steps for the improvement. By average, roughly each of us will produce about 1 kg of waste per day. And as you can see, the growth is more than 50% by 2025. It is expected to escalate to 2.2 billion tons. According to the latest report published by World Bank Group, usually they publish very good data on the global solid waste. This article was published in the year 2018. What a Waste 2.0. As we can see, food waste comprises around 44% in the municipal solid waste. And most of the technology or the treatment methods are still relying on open dumping, landfill, sanitary, with less than 10% of sanitary landfill. If you look at recycling and composting, these are less than 20%. This is talking about a general view on global scale. I like to draw your attention for the cost for waste management. Mainly, it includes collections, transportation, treatment, and finally the disposal. Interestingly, transportation costs and the labor costs could account for up to half of the entire waste management costs. And each of us will pay around 35 USD to 170 USD per year. Looks quite small, the number. However, most of the cost is actually covered by the government up to 50%, meaning that most of us as a taxpayers are paying this cost. The worst is that this is not giving us more products, okay? If you look at the landfills, ideally we want to have this sanitary landfill, as the waste will produce, we call it leachate, which is a liquid generated from the waste. Ideally, this should be treated before discharge to the underground water body to avoid potential contamination. But for most of the countries around the world, especially those low to medium income countries, the waste are still being sent to the open dumps. If we look at how we can treat the waste, basically we can divide into dry waste and also wet waste, or we can just call it as a food waste. If we look at the dry waste, these are typically, if recyclable, will be sent to the MRF, material recycling facilities. These are not so much a problem, yeah. For example, metal, glass, plastics. Okay, plastic is a big problem nowadays. Papers, they can be stored at a place until further treatment. However, for food waste, even for one day, if the garbage truck does not come to our housing area, we will be so worried about it. So this is one of the photo proposed in the report of Water Waste 2.0 by the World Bank report. Ideally, if we could centralize composting facilities such as this one, we can greatly reduce the waste management cost. However, still labor cost. Who is going to work on this kind of unit? Everyone is so busy nowadays. Virtually anything that's degradable can be composted. I always like to say there's no waste. It's just being misplaced. Especially those food waste, they are actually providing. It could provide nutrients to our Mother Earth. In the nature, if you look at this cycle for carbon, most of the degradable materials can be composted, be it on the land or in the sea, could be degraded into smaller molecules, and this will nourish the soil, the plant, and continue the cycle. In many countries, policy are driving towards circular economy, notably based on bio-waste. If we look at this ecosystem, most of the food waste and also organic waste produced by the farm can actually be recycled, most commonly as a compost, and this could be used in the farmland to grow wholesome food for us. I always like to stress that compost is not just NPK, okay? As compared to the chemical fertilizer, the modern agriculture have relied on so heavily. If we could recycle some of this food waste, compost, to our agriculture land, there are so much of the value proposition we could do to promote the economy. In the next few slides, I would like to quickly share some of the best practices, some of which I have also visited. The first one is a case study in Shanghai, China. As you know, since last July, China has implemented mandatory waste segregation since 1st of July. And I have the fortune to visit one of the composting plant in Shanghai. Okay. The idea I would like to share is how food waste, if being collected properly, can be recycled back to the farmland. So, from the visits, I have the fortune to learn a wide range of products being formulated, which are derived from the food waste. This is a PPP project, okay, public-private partnership. The products supported by an intelligent lab where each product is formulated to cater for different type of plants and also soil. It will also involve long-term analysis of the soil before and after the use of the food waste compost. As I only have 20 minutes, I will try to make it as short as possible. So in order to promote value-added products from food waste, there should be a framework. For example, through the usually we call it PPP, public-private partnership. I like to also add in community because this is where waste is being segregated as source. As you can see, it will involve many stakeholders, including the local government, which can come in to assist on the transportations. As you can see from my first slide saying that labor cost and transportation can account for up to 50% of the entire cost. So the role of the local authority is very important. It will also facilitate the collection of the food waste from the community, either a household and or the restaurants. And importantly, this cycle also needs the support from the university, the researcher, to research into the quality of the bio fertilizer, we call it, okay? The second case study is a farm called Follow, located in Johor Bahru, Malaysia, where my students have also visited. This is run by a local farm with support from a few corporates through their CSR. So again, this is a good case study of showing that food waste can be composted into solid compost as well as the liquid fertilizer. I have also been to Surabaya a few times. They have close to 30 composting house. They call it rumah compost, composting houses in Surabaya. One of the, I call it, most sustainable cities in the world. They facilitate many decentralized collections and composting throughout the city. If we look at the case study, they also receive a strong support from the NGO. And this product is being applied to the landscape in the city. So if we look at the critical factors to promote the long-term development of a bio product which are giving us more value, we need this kind of ecosystem to make it to happen. Then university researcher will gain more momentum to research into higher value products. So the concept can be summarized in this figure. Of course, there will be research at the university level. There should be financing instruments and enabling policy from the government. Let's look at some fundamental research we do in our group. If we look at the mixed waste, if the food waste come from a mixed municipal waste, it will be more difficult to commercialize the product. Okay, so ideally, the case will be that the food waste should be segregated as source, which is free from heavy metals contaminations. So on the right hand side, you can see a range of the challenges. Yeah, we need to know what are the nutrients content in the product. Then it can be formulated, standardized, and the quality being controlled. So talking about the food waste, in fact, if we want to mobilize the business for food waste to value-added products, we cannot just look at the food waste. We have to look at a wider range of organic waste from the cities up to the agriculture land, industrial waste from the food industries and also from the sewage treatment plant. Okay. As for the wet food waste, some of the major problems are oil and salt removal. Okay. However, I always emphasize that we can start with those food waste which are not so problematic. For example, those waste we can collect from hypermarket or from the wet market, which are not contaminated with oil and salt. If you happen to come to UTM, I will bring you to this community composting plant. Our group established since 4 years ago. There is ongoing composting work happening by around 30 households. Every week, food waste will be collected and the compost and liquid fertilizer are analyzed on long-term basis. So in our group, we analyze intensively the nutrient range in the solid compost as well as we call it bioliquid. As a biochemical engineer, I don't call it as a leachate. Leachate means it sounds like a waste. However, for bioliquid fertilizer, this is a kind of waste liquid leached from the solid compost, which are still rich in nutrient. As you can see, in the liquid form, the nutrient value for NPK are much higher than the compost. Why? Because they contain all the readily degradable nutrients. However, for the solid compost, the advantage is that it will slowly release the nutrient to our soil. Okay, so our team collects nutrient range for different type of waste, and these are just some examples. And further on long-term basis, we would like to know what kind of the relationship between the nutrient in the compost as compared to the bioliquid fertilizer, because analysis are easier for analyzing liquid than compost. If we have this kind of correlation established in the long run, we only have to analyze the nutrient in the bioliquid fertilizer, then we could predict what are the nutrients in the solids. So when we talk about closing the loop, for food waste to become the value-added products, we are not just talking about R&D. Okay, we have to look at the entire ecosystem from the top down, from the waste segregations, to at the end, who is going to buy? If we don't have the buyer, we cannot call it as value-added product. So even we also need experts from a wide range of discipline. Even we should make full use of IoT, Internet of Things, to monitor the quality of the soil before and after the application of the compost, for example. So as I can see, there are so much opportunity to how to realize this value-added product from food waste. As Dr. Mimi mentioned, I am one of the associate editors from Journal Cleaner Productions. So I welcome you to submit high-quality paper. Now the impact factor is already over 7. Every year also, our team conduct low-carbon conference. We call it ICLCA. Please feel free to Google on our website. This year, it will be held in Shanghai on 1st to 2nd of September. And finally, I would like to welcome you to visit our team in Johor, Malaysia, where I can bring you to visit the community composting plant. Of course, I'm happy to receive more questions. Thank you for listening.
Okay, great. Thank you very much, Professor Lee, for opening up our eyes and mind on the potential direction towards converting the massive food waste that we have now in many countries into products that bring new values to the consumers, as evident from your trips to several countries that you showed us throughout your presentation. those countries, we can see how successful they are in practicing food waste composting. And especially on the illustration that you showed us on how those nutrients from the food are actually not a waste, but they are being misplaced. So I found that as very interesting. Thank you very much again, Prof. Lee. So now let us welcome the second speaker, Professor Amjit. So Professor Amjit Panesar is currently a Dean of the Research and Consultancy in Saint Longawa Institute of Engineering and Technology, Punjab. He has more than 23 years of teaching and research experience in the area of food biotechnology. His research is focused in the area of value addition of food industry byproducts, green extraction of bioactive from food industry byproducts, food fermentation, and food enzymes, among others. Professor Panessa has received several distinguished awards throughout his career life, including the Young Scientist Fellowship by Punjab State Council for Science and Technology, India. He has published more than 135 international and national scientific papers, 50 book reviews in peer-reviewed journals, and has authored or edited around 7 books. He is a member of the editorial advisory boards of several national and international journals, including the International Journal of Biological Macromolecules and Journal of Food Science and Technology. So today, Professor Panessa will be talking about valorization of food industry byproducts for biopigment production. So Professor Panessa, similarly, you have 20 minutes for your talk. We're full of honor. Please welcome Professor Panessa.
Professor Utilization, Professor Lee, Professor Noyes, faculty and dear students. I on behalf of the slide welcome you all to this lecture and very good afternoon to all of you. I think I'm audible. So my topic of the lecture is valorization of food industry byproducts or biopigment production. First of all, that is about my institute, about the academic structure, about the sector has told about all the things. That is what we are and what we are doing. And basically, my institute is located northern part of India, in the Punjab state. 100% institutes, University of
Professor Panessa, we cannot really hear you. Can you, adjust your mic or something, because we cannot hear you properly.
Okay.
Still not clear. Maybe
Now, is it fine?
it has echo. It has echo. Your voice has echo.
And you can just check now.
Okay. What about the others? The other participants? Is this okay? The audio quality echo, right? I think so too. The others also. Okay. All right.
Can you use headset or something like that?
Yeah. Professor Panasa, do you have a headset?
Is it fine now?
What about the others? Can you all give some input? Yeah, echo problems.
Yeah, we can hear Dr. Panisar. Yeah, we can hear Professor Panisar. Yeah, it's fine. Seems fine.
Is it fine?
Okay,
Yeah,
this is
seems fine.
better. This is better. Thank you
Okay.
very much, Professor Panasa. Yeah, please continue.
It's
Okay.
it's
Thank
okay
you.
now. It's okay.
Thank you. Thank you. So, as for the my topic is concerned, that is the valorization of food industry byproducts or bypigment production. Pigments, we all know these are group of compounds. They are intensely colored, and colors they are always attractive. Whether to talk of the colors of the rainbow in the sky, or any dressing table, or food we eat. Color is the most important factor for food acceptance if we are talking about from the food technology viewpoint, and it is extensively used in every field, such as food processing, the textile industries, paper production, agriculture practices, and even from the color, a consumer can also judge the quality of the food, even that is whether it is good or whether that is some problem here. As far as the different types of pigments are concerned, we can classify on the basis of the source of the process. There are natural synthetic pigments are there, and the other are on the basis of the chemical structure. They are organic and inorganic. They can be another type of the pigments. Synthetic pigments are basically they're relatively simple, made by the relatively simple chemical reactions, mainly by the oxidation, and they are popular due to their cheap price, temperature stability, and high resistance power to the heat and as well as light. And different examples are there, we know about that. But there is a need to replace these synthetic pigments. The reasons behind that are well known. This slide gives you a summarized information that why we are concerned with the synthetic pigments. Basically, they have the low purity, they have even carcinogenic effect as well. Toxic properties are there, food allergies are there. They can do the DM damage. Even there are disorders like attention deficit hyperactivity disorder. Then behavioral problems are there, depression is there, habit and migraines there, and even there are some case studies in that as well. So there are the issues with the synthetic pigments, basically. And what are the alternates for that? Alternates are the biopigments. Basically, they are expected from. Hello. Pardon? So they are generally extracted from fruits, vegetables, and roots and microorganisms, and often called biocolors because of the biological origin. So they give the bright and intense color to the product, and naturally we know that is color is associated with the food we eat, such as the apple is having the red color, the lemon with the yellow, and carrots with the orange. So typically we eat the different types of colors in our life. They are safe because of their no toxicity, no carcinogenic effect, and biodegradable nature. So even they have some health properties as well. That is antioxidant activity there, inhibition of mutagenesis, and enhancement of the immune system is there. So basically, the different advantages of the biopigments are there. So as per the concerned classes are of the biopigments, there are carotenoids which have orange, yellow, pink, red color, flavonoids, purple, blue, red, and yellow color. Then vitamins are there, and then chlorophylls. We know this greenery all around, and that is all due to the chlorophyll and the green pigments there. So the color spectrum of the biopigments, if we see, we know that is basically the color compounds. They are about 400 nanometers. Anthocyanins, they have the big length between the 400 to 450 nanometers. Chlorophylls around 500 to 550. And anthocyanins, basically, they are around about 625 to 700 nanometers. A different wavelengths are there. So under this category, anthocyanin, vitamins, and carotenoids are there. So this is the color spectrum of different biopigments. So the around the biopigments, basically, I will discuss on the two categories. They are plant pigments and the microbial pigments, basically. So plant pigments, we know about the turmeric, and it has a pigment in that is curcumin, and it give you the white lemon yellow. I have marked the blue color, blue test, the purple one, and yellow one on that. Tomatoes, they are having the lycopene content, and it has the orange color, orange red color. Then beetroot, that is vitamins and pink to red color. Then grass, we know we are the having the greenish color in that. So these can be structured from plant pigments. So our second one is the micropigments, and much of work has been carried on for the selection of the pigment from bacteria, fungi, etc. So mainly the research has been done on the organism which I have marked that blue in color, Fabia, then astaxanthin pigment, and it gives the red color, then monaskis, and it gives a mesclavermin, and gives the yellow and orange red color, different depending on different pH and that. So then the Rhodochroma glutinase, and it also gives you the orange red color, even yellow color, that is selected depending upon. We can vary the pH of the medium quarterly, and we can have different types of color that is the micropigments. So much work has been done on monaskis and then on the reticulata. These are the possible alternatives when we say that is we have the choice of the synthetic pigments, and how we can replace them with the natural source or the natural pigments. Yellow color, we know that the sunset yellow is there. It can be replaced with turmeric, and beta carotenes are there in the nature. And orange can be replaced with the beta carotene paprika. The red can be replaced purple particularly with the anthocyanins and beetroot aspect. So these are the possible alternates where we can work on that. So these are the where we can have the combinations for the black. Then we can do the combinations for the green as well. So these are the possible promising combinations we can work on that. However, again, we have the major issue with the biopigments, that is the economics of the biopigments. Naturally, there may be questions in the mind of the audience. That is, we have the biopigments, where are those? But major issue is the economics of the process. And you can just see this review. I have marked as renal et al. Process biochemistry 2013. He has emphasized on the economics of the biopigment productions as well. So we can see, just giving one example, that is beta carotene produced by bacteria has an approximate cost of $100 per kg against the $500 per kg of synthetic meat. This is the one example of that. So research is being now carried out how we can reduce the cost of these biopigments. Naturally, there are one is the strain improvement, and the another area is that is if we can lower the cost of the raw material, then that can be an addition to the process. Like cheap agro-industrial residues or raw materials can be used as the substrate for the fermentation processes. So we have abundant of agro-industrial waste of byproducts which have been generated, and approximately it is known that 50% of the total organic industry pollutants are generated. And mainly in the food processing industries, they generate huge quantity of the waste and byproducts. So there, as we know, and even in that particular lecture, where our director is told that they are disposed sometimes, and it is a problem to the environment. So naturally, the treatment can be an value addition to this processes. And just this slide give you an overview. What are different byproducts? What are the industry in the food technology? Like cereal industry, there, beverage, alcohol industry, there, vegetable, dairy, sugar, meat, fish, and poultry. And what type of byproducts generate is a long list, and these are generated in different operations like starch, solid grains, flour, then wheat bran, and spent grains, release. So these are all different, and even fruit and vegetable we know that is different byproducts is generated, and even in our kitchen we use only fruits and vegetables, and lot of byproducts are generated. Even kitchen is a small industry, fruit and vegetable industry. And we can imagine when we put together the material from the different houses, how much waste is being generated. If we can use in some other way, like previous speaker has discussed the different means, like vermicomposting is one of the way. And other areas are there, we can use that. So if we focus on the characteristics of the agro-industrial waste, so these are organic and biodegradable and contains high amount of the lignin, cellulose, pectin, fibers, pigments. So naturally, they can be actually assimilated or used by the different microorganisms. They can be good substrate, and even they can also be used as a substrate for destruction by the conventional and the green techniques. So these are the ways where we can do that. And if the pigments are concerned, how we can proceed from the biopigments. So depending upon the source, we can go for the two approaches. First approach is that is we can use the different chemical, physical, and green extraction techniques. And another is the biotechnological approach for the section of these pigments. And this is an overview of different technologies which are being used, like in extraction method, conventional, it was oxidation and maceration. Under the green technologies, now ultrasonication, microwave, supercritical fluid extraction, enzyme assisted extraction, accelerated solvent extraction. So these are the different green technologies. Under the biotechnologies, we can go for naturally the fermentation. And under the fermentation also, there are two techniques are there, like submerged fermentation and salt-free fermentation. We can discuss about these in detail. Some add part depending on the amount, maybe the time allocated to me. So just with about the green extraction techniques, they are preferred nowadays because they require less amount of solvent as well as shorter extraction time, and they are more friendly. And different techniques I have already named. And depending upon the source and the scale up of your technology, we can use the different techniques, and all have advantages and disadvantages because time is less. So I am just taking these slides and focusing on this slide. It gives you an overview how to proceed for the pigment extraction from natural sources. That is, we have the source, then we can go for the pre-treatment, different treatments can be given, then we can go for the cell disruption and extraction, then sponification and separation, and what techniques we can use for the analytical for the purposes, that is for the analysis. So this is just a general layout of different applications we can carry in the extraction of pigments. Now, what natural pigments have already been extracted? This is the list giving you an overview that is different authors have used different byproducts, like tomato byproducts have been used, tomato waste, then pink sugar waste, then estrogens, lycopene, anthocyanins, carotenoids, and different techniques, combination of techniques can be used for extraction of natural pigments. As far as the biotechnological techniques are concerned, naturally, what are the major factors basically? I'm focusing on that. So, one is the bioreactor design, which bioreactor you want to use depending on the raw material, then microorganisms which we can use, then the type of the fermentation process. Like earlier also, I have told you that the two fermentation processes, generally solid state fermentation and the submerged fermentation, depending upon the raw material you are collecting from. That is where if it is having the high moisture content or the low moisture content, accordingly we can select this type of fermentation we can go for, and accordingly the name of this the selection of the microorganism. because of fungi basically they are more used in the solid state fermentation as compared to the bacteria. So accordingly, you can use the selection of the process and the selection of the microbial. This is again an overview, that is what steps will be there if you go for the biotechnological fermentation process for the biopigments. That is, first you have to collect the raw material, then sterilize, then selection of microorganisms. If you want to go for the genetic engineering other things, then you can go for the fermentation. Then downstream processing, that is also very, very important in the fermentation development, because we divide the categories into upstream processing and downstream processing when we're talking about fermentation. And finally, you can go for the formulations. So what are the benefits basically if we compare these two types of the biopigments? One is plant pigments and micropigments. And plant pigments, they have some disadvantages as well, but micropigments, they're preferred because they are more efficient, they do not have the seasonal constraints, they do not compete with the limited farming lands, and there's rapid growth is there. So we know that. So accordingly, this is a list where the work has been carried on the production of the micropigments. So in the micropigments, group has also worked a lot, and in the blue test, I have not used papers particularly. We have worked on the laudatory movements, then Nemescus, then apical nigram, and different fermentation techniques are used for the production of the carotenoid. You can refer on papers as well. So earlier also I told you that is much work is on the laudatory and Nemescus. So new organisms are also in process basically. So when we talk of the application, this is again a single slide focusing on different applications of these natural pigments. They are used in textile industry, dyeing agents we know. So I am just summarizing, I know the time is limited. So food industry, we know the food colorants and as well as to do the sensitivity, then human health, because they have antioxidant properties, as well as precursor of terminate can be used and it will be used to the immune system, and pharmaceutical also, because it has many health benefits as well. So just summarizing the things, the utilization of agro-industrial waste will not only reduce the process cost, but it will also help in environmental management. So we are in a win-win situation. Only thing is we have to take care how we can proceed. So as far as concerned, so market of color is increasing. As for the latest report, that is July 23rd, 2019, from Meticulous Research, the food colors is expected to grow as a market of CGR of 7.2% from 2018 to reach by $4.65 billion by 2024. So that is the growth in case of the pigments field. And different techniques can be used. What are the possible ways where we can give some inputs for the students also to work there, where they can work, because we have, these are the major areas where they can do when for the some input when the biopigment field, that is stain improvement can be done, we just screen smarter screening methods, then cost effective downstream techniques can be used, and metabolic, it is very coming in a big way, metabolic and genetic engineering, and microencapsulation and nanoencapsulation. These are the areas or the future areas where the work is needed for to increase different issues with the biopigments. So these are the suggested readings. This is one of the review which I have used this for preparing these presentations. It was a review that published in Current Opinion in Food Science, and these are the other references which I had followed. These are good reviews which students can follow, because in 20 minutes you cannot say all the things about the one subject, so you can go through these papers. So lastly, I acknowledge the UTMShine department, especially Dr. General, and also I thanks the speakers, Professor Idris, Professor Lee, and from Santalong Global Institute of Technology. I'm grateful for providing me all opportunities, and as well as the Honorable Director for sparing the time to address the gathering. And I'm also grateful to my colleague, that is Professor Manash, for spending the time. And this CSIR already gratefully acknowledged, because they have provided us funds to carry out some work on the biopigments. And I'm also thankful to the authors of the various manuscripts which I have used for preparation of this presentation. So thanks all, and I'm grateful to all the audience or students which are joined to in this webinar. Thank you. Thanks very much.
Professor Vanessa, for being very punctual, on time, right on time, and for sharing with us the great works that you and your team have done in producing biopigment materials from the byproducts found in the food industry. So especially on the bio-based or natural pigments, I think this should be further worked on as people nowadays become more and more cautious on favoring more on natural colorings over the synthetic colorings. And also we hope your talk will spark more ideas among other researchers to be more creative in manipulating the potentials offered by the food byproducts. Thank you very much, Professor Vanessa. So,
Thank you.
thank you. So our third speaker is Professor Ani Idris. So before that, let me introduce her shortly. Professor Ani is a professor in membrane technology. Her areas of expertise revolve around fermentation and downstream processing, as well as microalgae cultivation and processing. She received her PhD degree from UTM and Masters from University College London. She has won many research awards, granted with various research grants, and she also has quite a number of patents, and of course produced too many papers and other type of publications. Professionally, she is a certified professional engineer awarded by the Board of Engineers Malaysia, and she is also a chartered engineer, a title awarded by the Global Institution of Chemical Engineers. Today, she will be talking on an interesting topic entitled Extraction of Bromelain Enzyme from Pineapple Waste using nanofiltration membrane. Professor Ani, you have more or less 20 minutes. So without further ado, please welcome.
Thank you very much, Madam Chairman. And also thank you very much to the organizer, Associate Prof. Dr. Zainul, Chairman of the UTMShine, for inviting me as a speaker in this web seminar, UTM SLIT. And also fellow members, a very good afternoon to everybody. So I hope you all don't sleep during my lecture. My brief talk. This is just a sharing of knowledge. Basically, I'm going to talk about the extraction of bromelain enzyme from pineapple waste using nanofiltration membrane. This is actually a project that was actually given, granted from the Lembaga Nenas Malaysia, the Pineapple Board of Malaysia. It's actually to help farmers so that they can actually produce high value added products from the pineapple waste. Okay, the outline of my presentation is as follows. I'm going to give a brief introduction to the pineapple industry that we have in Malaysia. We'll talk about the bromelain and its applications, the methods of extraction of this bromelain, and we are using our membrane for the separation of this bromelain, which is the nanofiltration method. It's a one-step method, and probably we'll come to the conclusion. So just to give a little bit of background on what is bromelain, it's actually a group of proteolytic enzymes, a group of protein digesting enzymes, which is commercially extracted from the pineapple, either from the pineapple fruit, which is designated as EC342223, and also I'll call it a stem bromelain. And basically, bromelain is a mixture of numerous endopeptides of thiol and other elements of phosphatase, glucosidase, peroxidase, cellulose, esterase, and many other protease inhibitors. This is the structure of bromelain. A little bit of introduction why bromelain is because the bromelain market is actually growing. Is projected to hit US about 1.055 million by 2020, with a CAGR about 4.6%, and during the forecasted period of 2017 to 2025. And the total global production of bromelain per year is about 87,000 metric tons in 2020 itself. And the factor that affect the market growth are, why is it that is some of the factors that is being used in household care, is used in the industry, textile industries, in the health wellness. And of course, bromelain is what you call is a therapeutic benefits, and it's basically used in pharmaceuticals, food and beverage industries, and also in the cosmetic industries. So the world demand for bromelain market has been increasing, as you can see from these graphs down here. Okay? And in fact, in Malaysia also, you can see the demand for bromelain actually increasing. So the production of Malaysian pineapple, for example, what is basically about 33,543 metric tons in Malaysia. And Malaysia used to be the third largest producer of pineapple, but over the years, we have actually dropped to just one of the many producers of pineapple. I have a problem with my slides. Okay, right. So in Malaysia, for example, the pineapple is grown in various states in Malaysia. If you have been in Malaysia, then you know that some of it is grown in Johor, and then some of it in Selangor, Penang, Kedah, Kelantan, and also in parts of Sarawak and Sabah. And basically, it uses about 6.3% of the agro-food area in Malaysia, which is the fourth largest area after durian, banana, and rambutan. So in other words, it's the fourth placing. And basically, it uses is growing in area about 10,000 hectares, and it's estimated to actually increase. And then most of this pineapple are actually grown on peat soil, which is actually considered marginal for most agricultural products. And Malaysia at one time used to be, as I said just now, top 3 pineapple producers in the world in the 1960s and 70s, but right now it's only a relatively modest industry. Okay, so the varieties of pineapples we have in Malaysia are, like, we call it Morris, N36, Gandol, Josephine, Sarawak, Maspine, and also MD2. So the current variety that is mostly used now or mostly eaten is actually this MD2. is one of the sweetest variety, and this Morris is actually one of the not very popular variety because it's much less sweeter than MD2. So the reason why this project was actually done was because it's actually to help farmers who can't actually, in some cases they cannot sell their pineapple because due to the size and due to the undesirable characteristic of the plants and also the waste from this agriculture. So they are hoping that with this project you can probably help the farmers to actually increase their lifestyle, you see, improve the income, right? So, and we know that this Morris, for example, take an example of variety of Morris, you find that from 1 kilogram of pineapple, you can actually get only 56% of juice. The rest are all biomass, okay? And this biomass actually comes from the stem, from the crown, peels, and also pulp. And of course, in some studies, it was also shown that only 30% of the food only 30% of pineapple is actually consumed, but the 70% actually comes in the form of all these stems, peels, pulps, and also crown. So our aim is actually to look into the kind of bromelain content that you can actually get from the stem, the crown, the peels, and pulp, so that not only are the bromelain obtained from the juice, but you can actually also obtain the bromelain from the stem. Okay, so one of the very important things to look forward when you are harvesting your pineapple is that they have an index factor. Okay, so index factor is one of the very things that people look into when they want to harvest their pineapple. So usually when you have an index of 1, it means that the pineapple is not ripe and it has this what you call a very firm and sour taste, and it's not ready for harvest. And the harvesting usually starts actually when it has an index of 2 and is suitable for export by sea. When it reaches the index of 3, basically that is just nice for it to be actually harvested and is suitable for export either by air or by sea. The moment it reaches index 4, then basically it's only suitable to be flown by air, exported by air, or basically to be consumed locally somewhere close by that the farmers can just sell it off. Okay, so index 5 is actually very, very ripe, and it's only good for eating it fresh, and it's no longer suitable for export. So most farmers usually they will harvest their pineapple when it's actually at index 3 and index 4. Now, why bromelain is that bromelain, as I said just now, is a mixture of cysteine proteases found in the tissue of the plant family Bromeliaceae, and the proteolytic enzymes obtained from this pineapple can be obtained commercially, available either in the stem bromelain or fruit bromelain. In other words, you actually get this bromelain from the stem or fruit, and pineapples such as peel, core, crown are also reported to contain bromelain. So pineapple fruits contain proteolytic enzymes, bromelains, which can actually constitute nearly half of the measured protein in the fruit, and it's a mixture of enzymes derived from the pineapple. And why is that we are so interested in bromelain is because it has, as I said just now, these therapeutic benefits. It can has this what you call anti-edematous properties. It is anticoagulative. It has this antibiotic, anti-inflammatory effect. It has this what you call debridgement kind of effect, and also it's also known as to be has anti-cancer and also antithrombic. So it has a lot of benefits from this bromelain. So basically now we come to the how do you extract actually this bromelain out? There are several methods that has been used. Okay, one of them is what you call the aqueous two-phase systems, which is what is as called as a partitioning of proteins, or some people might call it as the usage of surfactants, okay, to actually extract the targeted proteins. Okay, in some cases, people has actually used PEG and certain salts to actually extract the targeted proteins, and most of it is usually used in initial stage of the process. So this is one of the process that has can actually provide also rapid separations and has a volume reduction. It's just that you have to add in chemicals to actually extract out the protein. And of course, we can also use the reverse micelle systems, which is a liquid extraction technique. It is also currently gaining importance nowadays. It can also handle higher loading capacity. It's separate. Its operation is rather simple, but there is what you call as a backward reaction and also a forward reaction. And of course, there's this what you call a different chromatography techniques that can be used. These are only meant for very low capacity, okay, and may involve many separation steps. And of course, you have this common one we call it the ammonium precipitation process, which is the cheapest process. But of course, when you use this cheap process, it has this disadvantage of the bromelain losing its structure and also its activity. So and it's also quite environmental polluting. So what we do in this particular study is to use what I call membrane separation, and people has now this is getting more and more attractive, and people has been using the microfiltration and also ultrafiltration, a combination of both to actually extract the bromelain out, and this membrane separation process is very unique in the sense that it has very high throughput of product, it's easy to scale up, it's very environmental friendly, and it's cost effective. So most of the researchers are using microfiltration and ultrafiltration. But however, in this particular project, we are trying to see if you can cut this two-step process of micro and ultrafiltration into using a single nanofiltration process. Okay? So we use our custom-made nanofiltration process to actually separate out our bromelain with the intention of actually reducing costs and getting high quality enzyme activity. So there are a number of steps that we do. One is that we extract the bromelain using our nanofiltration membranes, and then we quantify the bromelain activity at every single stage of the process, and then we also determine the stability of the extracted bromelain. So we have preliminary cleaning taking place first. We homogenize our pineapple. Then we remove the debris by centrifugation, and then we pass it to a nanofiltration so that we can get our bromelain crude extract here. So as you can see here, this is where we use an extruder machine to actually juice out our pineapple. So what we did in this one particular study, we separated out the core, the flesh, peel, stem, and crown separately with the intention of actually finding out if every part of it can actually produce bromelain, and we want to make sure that by using our pilot plant, by using our nanofiltration system, whether we can get the bromelain from all these parts of this pineapple. So the first step we did was to actually just juice out the pineapple, peel, stem, and crown separately, and then we pass it to a centrifugation. As you can see here, once after centrifugation, we have the supernatant layer at the top here, and this supernatant layer basically will then be passed to a nanofiltration here, where you can see here that you get very clean the clear liquid here, and you get our retentate here. So this is the filtrate and this is the retentate. And the type of membrane that we use is actually a polysulfur membrane with the size of about 10 to 20 kilodaltons in range. The filtration rate is about 12.5 sorry, I think it's 12.5 liters per hour at a pressure of about 1 bar. And after that, we analyzed the bromelain by using the casein, the digestion unit method. And after that, as you can see here, this is the feed to this membrane. And you can see the permeate here, and you have the retentate then. And then we then freeze dry our bromelain, and this is what we get our fine bromelain powder. As you can see here, the results are rather interesting here. We find that the bromelain activity, okay, for every single step, we find that there's an increment in the bromelain activity, as you can see here. So the bromelain, for every single part of the pineapple, you find that there is bromelain activity. So you can find that the highest bromelain activity is, of course, found in the flesh, which is the fruit itself. And the peel also gives very good bromelain activity. The core, followed by the core. So basically the flesh gives the highest, followed by the core, and then followed by the peel. And you have the crowns also have high amounts of bromelains. And you have this CWM here referring to a mixture of the crown, peel, and also stem. And you find that the range of the bromelain is in between the flesh and also the crown. So you have an average value there. So as you can see here, this is the bromelain for every step. As you can see here, that there's an increment in the bromelain. And then this is another part of it, whereby at the last stage of this step, you find that the bromelain content in the final product is rather high here. So this is the final product that you have with a high amount of bromelain content. And this is another study, and we check on the stability of these enzymes, how stable they are. And basically, we find that, of course, bromelain, the stability decreases over time, which is quite typical of any enzymes. And but then we say that the results indicate that in order to achieve higher specificity of this bromelain, the extract should be used as soon as possible or better to use it as a fresh extract. So in another study, what we did was we get some pineapple waste from the tin canning industry. This is much interesting, whereby this waste is actually produced by one of the largest canning industry in Malaysia. And we get it from them, and we actually try to see whether there's a sufficient amount of bromelain that you can actually get it. And the results are shown here. You can see there. So you can see that the amount of bromelain, here you find here there is this retentate. It retains about 176.75 CDU per mil, which shows that even the pineapple waste from this canning industry can actually be used to produce high value added products. And the process that we are introducing to them is that it's a one-step filtration process rather than using the other chemical methods of extraction. So this is one of the viable methods to actually use in order to actually improve the quality of the bromelain. Okay, so some of the details of this study is actually found from one of my published work here. This is from a Morris variety. So in conclusion, the nanofiltration membrane can actually be used to extract bromelain, and the results revealed that the pulp of the pineapple contributes to the largest bromelain portion for both the Morris and the MD2, followed by the core, peel, and crown. And the bromelain extract at every stage of the extraction is actually quantified, and the bromelain concentration increases after each process step, indicating that the concentration process has actually taken place. And the bromelain activity of the portions decrease slightly throughout the storage. However, this can be actually improved if you do a freeze dry and store it in a very, very cool place. So the pulp, core, and peel exhibit high bromelain activity. However, the peel is the major waste proportion and seems to have the utmost potential for bromelain extraction. So the waste from the pineapple canning industry show relatively high bromelain content. So on that note, I conclude my talk. Thank you very much.
Okay. Thank you very much, Professor Ani. Also for being on time. I really appreciate this kind of, on time thing. On time thing. So thank you, Prof. Ani, again for the great sharing on the technology of applying membrane in maximizing the potential that we can actually get from food waste. And from her context today is the pineapple waste. So as we know, bromelain is an important enzyme for our body functions, especially for protein digestion and as an anti-inflammatory agent. So to listen to this presentation today given by Prof. Ani, we cannot thank you more. Thank you, Prof. Ani.
Sure.
Yeah. So, okay, now, last but not least, the special one, we would like to welcome Professor Avinash Thakur. Professor Avinash is the head of the Department of Chemical Engineering at San Longowal Institute of Engineering and Technology, Punjab. He has 23 years of experience in teaching and research. He is a lifetime member of the Biotechnology Research Society of India, as well as the Indian Society for Technical Education. His research is focused in the area of biochemical engineering and downstream separation processes, especially green solvent extraction and value addition of agro-industrial waste. So this afternoon, Professor Avinash will be giving a talk entitled Utilization of Molasses for Lactic Acid and its Separation Techniques. So without further ado, Professor Avinash, again within 20 minutes, please welcome. Yep. So I believe Professor Avinash is working on the audio, yeah?
Can't hear anything.
Yeah, he's working on it. I mean,
It is not audible.
can you try to speak, Professor Avinash? Is he already presenting?
No, ma'am.
Okay. Okay, please do not leave yet, right? I mean, I think Professor Avinash, the topic is very interesting, so let us wait together, but I hope he can figure it out soon because we have quite a number of questions, so we also would like to open for the question and answer session. Or should we ask few questions before Dr. Avinash can, you know, make the audio works?
Hello.
Hi, yes.
Hi, myself Dr. Pankaja Shukla from Bhopal, Madhya Pradesh, India.
Hi, Professor Panka. You would like to ask some question?
Yeah.
Okay, please. I think Professor Abhinesh, when you are ready, just interrupt in, yeah. So as for now, we allow for some question and answer to save some time. Okay, Professor Panka, you can post your question. Yeah.
In South India, South Indians do not prefer pineapple. They say it is a abortion-inducing fruit. Is it true or it is a taboo?
So I believe your question is for Professor Ani, yeah, on the pineapple.
Yeah.
I do not think. I think it's I mean, different people react differently to certain things. You see, to some probably it has this probably this effect on some people, but generally it does not have most people do not have that such an effect. So I don't think it's a taboo. Probably to some people, yes, but it's not a something common to everybody. In fact, the benefits of this probably is much more than what as the taboo that has been mentioned just now.
Okay. Thank you. Thank you so much.
Yeah, welcome.
Okay, thank you, Prof. Ani. So, and another question that we collected from our Facebook chat. I think this is for Professor Lee. Is there any collaboration between UTM and local town council, for example, Majlis Bandaran Iskandar Putri, in food waste collection from community? And do you guys send it to the composting plant? If Professor Lee can give a short and precise answer.
Thank you so much for the questions. We had some discussion with a few PBT local authorities around UTM. In fact, one of the project is almost getting there. We have already found the land and the farmers to help us do the composting, where the food waste will be collected by the local authorities. However, the project did not get started due to unavoided circumstances, including change of government a few years ago, and also MCO. But surely we look forward for this kind of collaboration to make food waste recycling to happen in our region. Thank you.
Thank you very much, Prof. Lee. And also, there is a comment by Mr. Bilash Chandra Roy mentioning that Tripura, a small city in India, is producing bulk amount of pineapples. So he suggested that perhaps UTM and SLIT or maybe the Indian side could somehow work together to collaborate in this pineapple waste related study. So I would like to suggest that Mr. Bilash, you can see Professor Ani email, right, in the WebEx chatting media. You can directly contact her, yeah, to initiate on the collaboration. Yeah, thank you. Okay, Professor Abhinesh. Or I can hear some voice. I don't know from who. Okay, there is another question from Dr. Ruby to Professor Lee. So the question is, how about the sludge treatment in petroleum industry by microorganism? Have this been done before? Sludge treatment in petroleum industry using microorganism.
Thank you for the question. I'm sure this kind of area has been studied ongoing, including bioremediations using different types of microorganisms to degrade oily stuff and also plastic. And some even they might use genetic engineering to find out the most potent microorganism. Typically, this kind of microbe can be isolated from the oily environment. Again, everything will come back to economic feasibility. Yeah, how fast, how much. Yeah. And I do not have. Yeah, thank you.
And what about, is there any specific microorganism is undergoing, on study?
Specifically, I do not look into it because most of my research are in the area of food waste. For example, if we want to degrade food waste, we will have to isolate the microbe from the food waste itself. Okay. If we want to degrade fibers, we have to find the microbe from rotten woods, from the forest. Yeah, likewise, for the oily sludge, even for petroleum base, it should also be isolated from the ecosystem, similar ecosystem itself. Okay, I'm sure you can easily screen from the Science Direct, any search engine to find those papers.
Okay, thank you.
Thank you very much, Prof. Lee. And there is also several questions on, is there any food related courses or program offered in UTM? So maybe I can answer that on behalf of the others. So basically, for undergraduate program in food from our school department, we don't have that. But next year, there will be a new master's program on food processing and innovation. Starting next year. So we would like to welcome you all who are interested to join the program. And in terms of research, of course, we have several professors and experts here who are doing studies in food technology and maybe food waste and this kind of thing, including, of course, our Professor Professor Ani Idris and Professor Lee, and we also have Professor Ida Idayu and the other junior lecturers who are working on this subject matter. So, okay.
Yeah, am I audible now?
Professor Abhinesh? Okay, good.
Yeah,
Can hear you clear and clear, right? Good.
Yeah. I want to actually upload, share the screen. So kindly allow it from the Dr. Panesa's laptop, please.
Okay, please start.
Okay.
Yeah.
Kindly allow me to share basically on from the Dr. Panesa login ID to share my slides. Okay, thank you. Thank you. So I'm getting it. Okay, thank you. Thank you. Thank you. So I'm getting it.
Ada sesi.
Okay. Am I audible to all?
Yeah.
Sorry for the interruption. I thank for the patience and I thank all. Okay, so back to my topic basically. So utilization of molasses for lactic acid production and its separation techniques. Okay, so historical basically lactic acid was discovered in sour by Shea in 1780. It was produced commercially in 1881 by Charles, USA. It has got two optimal isomers, L-lactic acid and D-lactic acid. And the application of lactic acid obviously in food industry for consumed in many foodstuffs, it plays an important role in food preservation, shelf life, flavor enhancement. Then as a biodegradable polymer, lactic acid is also an important substrate for the production of biodegradable polymers. Polylactic acid particularly, which has got numerous applications, and it's a biodegradable polymer also. And the pharmaceutical industry, if I say the drug delivery, it is utilized. Then then it's a cosmetic industry, then chemical industry as a raw material. Then demand of the lactic acid is huge. Basically, in the coming year, it's going to rise up. Worldwide demand for lactic acid is estimated roughly to be 130,000, 150 metric ton per year. And by 2020, if you say that over 1 million ton annual production of lactic acid for the conventional markets and PLA. Considering the lower market and agro-based chemicals hold a promising future. Lactic acid production methodology, if the chemical synthesis, one is the chemical synthesis, but it results in the racemic mixture of D and L lactic acid. Then and fermentation. By the fermentation, we can get the L, D, and DL mixture that can be produced using the specific microstrain. About 90% of the lactic acid is produced by fermentation. Production for polylactic acid, which I had already talked, that is a biodegradable polylactic PLA. This is fast optically pure lactic acid. Then production sequence means there's the two lactic acid production includes two key stages. One is the fermentation, another is the product recovery. The recovery and purification influences the quality of lactic acid and its final price. Then we come to a topic that molasses as a substrate for the microbial production of lactic acid. So cane molasses I utilize for the research work, that is again that's a byproduct from the sugar manufacturing process of sugar cane left after the removal of sugar from the mother syrup. It's an inexpensive renewable raw material. It's a great source of carbohydrates along with other essential nutrients and stimulates the growth. Used for the production of number of industrial important chemicals like ethanol, sorbitol, and acetic acid and polysaccharide. Lactic acid can be produced using the bacteria and fungi. Over 90% commercial lactic acid produced by the lactic acid bacteria. So there are three metabolic categories according to the assumption. That is, one is the obligate, homofermented, obligate wild, and cultative heterofermented. So homofermentive lab can include the list, and then but the homofermentive lab produces the major product as lactic acid, while the heterofermentive lab produces lactic acid, carbon dioxide, ethanol, and acetate. There are the different factors. So if I talk about the molasses basically, so molasses have the characteristics. Then this is density, then the total sugar is about 52%, reducing sugar is about 56%, proteins, total nitrogen, dry matter, ash content, and pH is about 7.8. Now we had because utilized different types of microbes to find out what is the efficient microbe which can produce the lactic acid efficiently. So there are lactobacillus platform, the lactobacillus and the acai and the platform. So different strains have this, and there are different factors which we had checked for the to check the influence. So one is the very first factor is selection of the microstrain for the lactic acid production. Then effect of the nitrogen source. Different nitrogen source can be utilized for the growth of the. After obviously for the selection of microstrain, our work we had found out that LDSI is the best one. So we utilize this particular for the research work. And in different nitrogen source has been utilized for the finding of which one is the effective. Then positive liquid, another base which is, we had find out the best one. And then the nacrodome size is another factor. Then the constant liquid concentration, another factor which can be checked by the production of lactic acid. Then the sugar content, what is the effect on the by the microbial effect, what is the sugar content effect on the microbial production. Then the incubation time. Then calcium carbonate, obviously, which has been added to just maintain the pH inside pH of the fermented media. Then magnesium sulfate, another we had utilized as a supplement. Then effect of the pH and the incubation temperature. These are the 10 parameters. There can be other parameters also which can be checked by the production of the lactic acid from different raw materials. So there can be other raw materials also as well. We are talking about the molasses, the whey, other waste material. Then the potato peas. There can food waste. There are a number of other raw materials can be utilized for the production of the lactic acid depending upon the strength of a particular microbe to convert the particular starch or any sugar content into the lactic acid. So based on all these parameters, we have checked and we had find out the significant effect on the molasses. That is the sugar concentration, CSL concentration, and the pH and the incubation temperature and the incubation time, which has got a significant effect on the lactic acid production from the molasses by the Lactobacillus casei. And then we had decided to do the optimization, what should be the optimum condition and where we can get the maximum lactic acid from it. So we had applied the central composite rotatable design. You can also, there are certain other designs also available with the response surface methodology as a DVD, Gauss method, a 2F factor method. So we, in this case, because it gives us the 5 different levels, means 5 different concentration I can choose for the sugar concentration, for the constant liquid concentration, for the pH. So based on those experimental design we had conducted the experiments, and then we had find out and do the analysis, that the ANOVA analysis of variance and the interactive effect of the 2 variables on the lactic production we had analyzed, and we had after that we had done the numerical optimization. And after doing the optimization, we had found out that if for the sugar concentration of 190 gram per liter and the CSL concentration of 2.75% volume of volume and pH of 6.75 and the temperature of 38 approximately, and after 60 hours of incubation time approximately. So we were able to find get the micro optimization technique had predicted that 119.45 grams per liter can be produced from 190 gram sugar concentration. After doing the confirmation experiment based on the optimized condition, we had find out that it is 116 gram approximately ±2, which has been produced from under the optimized condition. So this is with the free cell of the lactic acid production optimization. Then another we want to enhance then another cell immobilization. So we have taken up the cell immobilization. Also, cell immobilization has found numerous applications in different industries, such as food production, agriculture, wastewater treatment, pest control, environmental decontamination, production of theoretical agents, enzymes, and biofuel. Cell immobilization also has the great potential for coupling fermentation and separation that enhance the tolerance and efficiency of the microorganisms, simplify the process and lower the production costs. This particular technique, basic immobilization, is we found it also helpful when we talk about in situ fermentation. We'll talk in the later on slides. And then provides an advantage such that during the extractive fermentation of lactic acid, organic solvents could not damage the bacterial cell because there can be adverse effect of the solvents on the bacterial cell. And it's a promising technique for easier separation of the biomass from the fermentation medium. So with this, again, we have to screen the matrix. There are a number of polymers available in which the microbes can be entrapped. So we tried with sodium alginate, cytosine, and then carrageenan, and then the combination of PBA, alginate, and PEG and alginate. And then we had there can be other factors also, but we had to check the effect of these 11 10 variables of other effect of immunization matrix. So we had find out that alginate was giving the best result. So we had again checked the effect of the alginate concentration. Then the coating. In order to basically decrease the lease of the microbes from the immobilized yeast, we had done the coating with the chitosan. So that is subsequently chitosan alginate, that is ECA, then with chitosan alginate. This is triple layering. So we had find out that ACA is the best one, basically with the alginate, then chitosan, then the alginate. So after then the effect of the bead size has been checked, then effect of the immobilized biomass content, how much content we can entrap in a particular material, the amount of material, then effect of sugar content, then effect of the constant liquid concentration, the agitation speed, then temperature, and the effect of pH. And then reusability of alginate bead also. We check how many times we can reuse the particular beads for again and again production of the lactic acid repeatedly. So based on that, we had find out that there are again 5 factors which were significantly affecting the production of lactic acid from the molasses with the immobilization. One is the sugar concentration, and the pH, then the biomass loading, and then incubation temperature and time. Again, now we had again applied the BVD design, working with the response surface methodology to find out the optimal condition to obtain the maximum lactic acid production. So under this condition, we had find out the optimal value for the test variable were 186.5 gram, and the biomass mole was 285, that is on the dry basis, and 6.6 was the pH, 37.5 degrees centigrade incubation temperature, and 58 hours the incubation time, and we were able to achieve 130 gram per liter, which is higher than the free cell fermentation, which was 116 approximately. So we get more 14 gram higher production of the lactic acid with the immobilization. So with this, then we had tried, because with the continuous process, also continuous production in 2 stages. Again, we had used in the fermenter. Then we had put in the one CSTR. After CSTR, we had arranged a packed bed reactor, and we had find out that how the effect of the dilution rate on the production of lactic acid. We have find out with the increment in the dilution rate, obviously production kept on decreasing basically. And in the second stage, he says that because volume was lesser, if you see the volume in comparison to CSTR was somewhat lesser. So when the dilution rate was very low, that is 0.05 per hour, we were able to have the increment the lactic acid production from 10% and then 8% and 5% when we were utilizing sugar of 175, 150 grams per liter. So this is how lactic acid can be produced from the molasses, which is obviously agro-industrial based using the lactobacillus microbes. So after then, what the challenge is, that means production is effective. The challenge is that that it's a difficult downstream separation process. How to separate the lactic acid? Why? Because there is end product inhibition. As lactic acid concentration increases, productivity decreases. As pH increases, unnecessary lactic acid binds with the binding site of the enzyme, and that got the reduction in the lactic acid production. So that is the effect of the pH on the lactic acid production. So, what are the product recovery approaches for that basically? So, one is the classical approach. Okay, so one of the classical approaches is basically acid precipitation with calcium hydroxide, and then treatment of precipitate with sulfuric acid to give the free acid and calcium sulfate, and free acid purification by filtration and evaporation to use acid-like acid. But it has got certain disadvantages. Complicated and the yield is low. Method do not show enough purity, and the residual sugar and the nitrogenous compound are also precipitated. Disposal problem: for every mole of produced acid, a mole of calcium sulfate is created, and separation purification of lactic acid can be up to 50% of the total cost. It's a very expensive process. So other approaches is on extraction, but low activity of lactic acid molecules toward the water causes low restriction coefficient in organic solvents. Then ion exchange resin, high cost, low capacity of resin limits the applicability. Evaporation, high energy consumption, water vaporization, electrodialysis, complex equipment tried by the contamination of biomass, and distillation, lactic acid is not normal. So there are problems with these all techniques. So there is one of the noble technique that the solution. What is the solution basically? Either you use a genetically modified cell or do the in situ extractive fermentation, right? In situ extractive fermentation features means simultaneously recovery of the organic acids during their production in the fermentation broth, and suppression of the end product inhibition and enhance the reactor efficiency. The novel technology which we lies for the lactic acid actually from the aqueous, then we had tried it with from the fermentation broth as well also. That's the emulsion liquid membrane. This has an attractive alternative to conventional solvent reduction due to high selectivity, ability to concentrate compounds of low concentration. Basically, it's a triple emulsion system. Water, oil, water, and oil, water, oil. The solute diffuses from, because basically in third phase, you see this is the receiving phase, and the middle one phase is the oil phase, and the outer phase is the aqueous. That can be a fermentation media. So what happens basically, so I will let you know, this is a schematic representation of precipitator mass transfer mechanism of the lactic acid permeation. Lactic acid from the external phase, we introduce a carrier in the membrane phase that can be a tertiary amines. There are other carriers also, but we utilize the tertiary amine. The tertiary amine binds the lactic acid at the external membrane phase, and it transports across the membrane phase due to the concentration gradient and goes to the membrane stripping interface. There, in the stripping phase, that the inner water phase of the emulsion, it contains sodium carbonate. The lactic acid reacted with the sodium carbonate forming sodium lactate. And but sodium lactate cannot diffuse back because the amine, which is the carrier inside the membrane phase, it doesn't allow the interaction or combination with the sodium lactate. Sodium lactate cannot diffuse back to the aqueous phase. So that means lactic acid got trapped inside the emulsion as a sodium lactate. So there are two unit operations which are taking place. One is the basically mass transportation, that another is the reaction. So those two simultaneous unit operation taking place in the liquid emulsion membrane simultaneously. So this is the schematic representation of complete emulsion liquid-based batch separation process. Here in the batch reactor, we prepare water and oil emulsion. Once we have got a stable butter and oil emulsion, we put in the basically fermentation broth. So fermentation broth, and then the diffusion table, it got the lactic acid trapped in the liquid emulsion. So this is the continuous emulsion liquid waste purification process. Here we prepare the emulsification using an emulsifier. Emulsifier should have the HLV factor less than 10 for the formulation of the oil, water in oil emulsion. So after the emulsion, we put in the fermentation broth. Then we take up the fermentation from the fermentation broth, the emulsion, because emulsion is basically what happens. It is lighter in weight in comparison to the fermentation broth, so it can be separated out easily. And after the emulsion taken out from the fermentation broth, it can be demulsified. And after demulsification, because emulsion is basically it contains water and oil, two phases. Oil and water can be separated out, and the inner water, that is what's the inner aqueous phase that contains sodium lactate, that can be taken out, and the membrane components which can be recovered and again utilized for the production of the liquid emulsion. So these are the basically some of the characteristics of the or the advantages of the liquid emulsion membrane. It's a large scale quality and availability, prepared using the simple material installation and equipment, combines both extraction and stripping steps into one scale, low capital investment and easy to operate, cost restriction, and then 40% less costly than solvent extraction process, high mass transfer area to volume ratio, 1,000 meters square per cubic meter. That is the key, that the process can be completed within a short span of time, within 10 minutes, low volume ratio organic of aqueous phase. And then major factor influencing the performance of the system is basically, one is the technique, basically by which technique you have formulated the emulsion, as ultrasonication or agitation, what is the speed of the agitation, then emulsification time, what is the droplet size, which kind of surfactant and desurfactant has been utilized for the emulsion, and then mechanical agitation, speed, internal phase, and the expected.
Professor Avinash, you only have 1 minute left, yeah?
Okay, I have got 3 slides more. So this is one. This is what we had utilized by extractive fermentation of the liquid emulsion liquid membrane. So this is the basically overview of the application of emulsion liquid membrane. Different organic acids have been utilized. So another factor which we can introduce in the emulsion liquid membrane, the green emulsion liquid. In place of using the petroleum-based organic in the membrane phase, we can use the palm oil, sunflower, rice kernel, mustard oil, coconut oil, and corn oil. These are economical, these are low cost vegetable oils. It can reduce further the cost of the emulsion liquid membrane technology. So based on this, these are particular characteristics of emulsion technology. This minimizes the waste generation, because in the other case we were using the petroleum base. This economic in nature, easily availability, no toxic to human health, reduction in use of toxic solvent, better future scope, use of renewable scope, resource efficient and environmentally benign. So here, if you say that this is a green emulsion liquid membrane had been utilized for the different, other you see in the other production from the fermentation, succinic acid, extraction of lactic acid, we have utilized the rice bran oil for them, then extraction of lactic acid by the sunflower oil. The people are also utilizing the vegetable oils for the formulation of emulsion liquid membrane for the extraction of the carboxylic acid from the fermentation process. So this is the novel technique which we are utilizing for the separation of the lactic acid.
Okay, Professor, you have to wrap up, yeah? Okay, thank you, Professor Avinash. Thank you very much.
Thank you very much. Thanks for providing the opportunity.
Thank you very much, Professor Avinash. So how we are going to do this, Dr. Zainul? Because actually we have a few more questions, burning questions, but we actually have 5 minutes more. Should we ask some? Okay, I think we ask before 4:30. Okay, one question from Dr. Sandram. Dr. Sandram to Professor Lee. Can wet quality waste like from broken cereal like maize or wheat be recycled? Professor Lee?
Hello, hi, thank you for the questions. When you say recycle, I presume you meant compost. As I mentioned in the slide, everything degradable can be composted to become compost to nourish the land. However, if the food is rotten, it might not be suitable to be recycled as animal feed, because certain fungi can cause growth development for the animals. So basically, if as far as compost products are concerned, any rejected food can also be recycled into compost. Thank you.
Okay, great, Professor Lee. Okay, we like that precise answer from you. And then next question, I think from Dr. Azira. Dr. Azira asking a very practical question, I think, which is relevant to all countries. How we should encourage food service industries like restaurant, food vendor, and hawkers to turn their food waste into wealth instead of throwing it away. I mean, anybody would like to answer that question? Or maybe this is a very generic question, right? I think this is something that we can read from somewhere or not to related to the research. So maybe I move on to another question by
Mini. I
yeah.
think Professor Avinash is trying to answer the question that you posed just now.
Oh really? Oh
Yeah,
sorry. Sorry, I
Yes.
didn't notice. Sorry, Professor Vinesh. Okay.
yeah, I'm there, please.
Yeah.
Hello, yeah, please.
Yes, Prof. Avinash, you would like to answer the question?
Yeah. I'm ready. Please ask the question, please.
Mimi, can you repeat the question, please?
Okay, so Professor Avinash, a question from Dr. Azira. How to encourage food service industries like restaurant, food vendor, or maybe hawkers to turn or convert their food waste into wealth, into value-added products instead of throwing it away?
Yeah, that is basically at the very initial stage when we are throwing the base, we have to segregate the base accordingly. And we should be identifying that which base should be first, as an investigator, should know that which base has to be utilized in which way. And then they should tell all the nearby the people of the restaurant people that you have to give this type of base to us, and you have to keep this base segregated from the other base. So segregation is the first, and then the storage is, and then transportation to the particular lab or the industry where it can be utilized effectively.
Okay, great. Thank you, Professor Avinash. And then,
Thank you.
yeah, another question from to Professor. I think I asked one question to Professor Ani first, given by Dr. Prasad. He is asking, does the bromelain enzyme, including the one that you produce using the technology, can be used in pharmaceutical industry? Professor Ani? Is she there?
Yeah. If the source is from the fruit, then I think is probably much easier to be accepted in the pharmaceutical industries. But if it's from the waste, then probably it can be accepted, but then it has to go through a series of other probably highly it has to be further purified to a much higher quality before it can be into a pharmaceutical product. But if it's meant for like nutraceuticals, probably as a moisturizer, as in the textile industries, then that's fine.
Okay, I think the answer is very clear. Yeah, it should come from the fruit itself rather than the waste. If it is going to be used as the high end quality type of enzyme in the pharmaceutical industry. And one question by Dr. Jodilin to Professor Lee. Since waste management is very important for the environment and to help farmers to produce high value added byproducts, wouldn't we be left with a concentrated residual waste after processing the preliminary waste? Will this give another arising risk in the future? Since some waste management require chemical for treatment, so is this going to add another type of hazard? I mean, or risk? Professor Lee.
Yeah, I think this question is a little bit open-ended because it depends on what kind of the waste we collected into our farmland. Typically, if we have already removed the crop, usually the leftover lignocellulosic material, which are not in which the nutrients are not so high in concentrations, which are typically okay to be recycled back to the soil. But if you are talking about accumulating extra food waste from other side, yes, of course, this will cause high concentration of nutrient at one spot. Then it is talking about how do we design the composting plant. If the compost product is too high in quantity, it will create the opportunity for commercialization. So it will be distributed or sold to the surrounding farm around the region. As for the potential hazards of the chemicals, it depends on what kind of chemicals are you talking about. Usually in composting, there is not much chemical that will be added. Okay. In fact, talking about chemicals, and there is also very likely that when we apply, it will involve combinations of chemical fertilizers as well as organic compost fertilizer in order to achieve a good productivity for the crop. Thank you.
Thank you, Professor Lee. So one question dedicated to Professor Panessa by Dr. Urvashi Agrawal. The question is, would you compromise the quality and health benefits of food for sustainable food waste management and utilization? This question is for Professor Panessa.
Okay, thank you. So basically, the demand for the processed food is increasing day by day, but sidewise the waste is being also generated. And if we want to compromise both the things, the production and the byproduct utilization, we have to be more focused on the byproduct waste minimization. One is the waste minimization, and second is the valorization. So two things we have to do side by side so that we can get maximum benefits from the waste as well. So over to me.
Okay, thank you very much, Professor Panessa. And I think actually we have exceeded the time of 4 minutes, but maybe one or two more questions to speakers. So to Professor, this is a question I think open to any of the speaker. In business perspective, whether these platforms may help to develop in the upcoming years, especially in South India. I mean, this kind of thing, will it help in developing, especially he asked in South India, from the business perspective, this kind of food waste utilization and management. Anybody, maybe from India side, can answer the question?
Yeah, thank you. As for this question concerned, I think it's the need of the hour. That is, we have to be very, very serious, or we should have concerns about the waste management. And whenever we can interact with the different universities are there, they can collaborate in different areas. One university may have strength in one area, and other university may have strength in another area. If they can work together, collaborative research is required. So basically, all is the waste management, not in the South India. It is the need of the world. That is, we have to work on that, and then we have to work in the collaboration. Okay.
Okay, great. And last question. Last question is by Dr. Prasad to Professor Panesar. The question is, the pigments which are extracted from fruits and vegetable waste, does the technology involved is less economical?
Yeah, I think Dr. Prasad, you must have seen my presentations. I had one slide which was on the economics of the production of the biopigments. So that gives the answer to you. Already I have discussed. I have also given a reference of 2013 paper in the process biochemistry by Dr. Daniel. So he have focused on what the economic issues are there and how we can improve that. And I have also given some of the suggestive measures in the last slide, that is how we can improve the economics of the process. We can go for some of the better technologies, like some of the green technologies may have the more efficiency. And then from the fermentation viewpoint, we can lower the cost of the substrate. We can go for the metabolic engineering, and we can go for the better downstream processing. Obviously, everybody knows that the cost of the biopigments is higher as compared to the synthetic pigments. That would always remain the issue. But to minimize, and I have well addressed those issues. Where and what are the ways by which we can improve the economics of costs?
Okay, thank you very much.
Sir, can I ask you one question, sir?
Okay. Yes, please. One last question.
Just a minute. Sir, the pigments which we are collecting from the bio waste, producing from the bio waste, is it heat sensitive or not?
Yeah, there are naturally, these are some of the issues that heat sensitivity and light sensitivity. There are issues with the biopigments. Okay,
so we cannot
complete first. Can kindly just let me complete first. But there are solutions to them as well. Because if we have some heat resistant organisms, we can improve the heat stability or thermal stability of the pigments. And there are other ways as well. You can go for the encapsulation purposes. You can improve heat stability or thermal stability of the pigments. So every problem has some solutions. Only thing is we have to work out how we can overcome those other barriers. Okay. Now you can speak, please.
Okay. Thank you, sir.
Okay, so thank you very much to the last participant who was asking the question. So of course we would like to entertain more questions, but unfortunately the time is up, and I would like to really thank all the great 4 speakers for giving us amazing talks and sharing today, this afternoon. And the topic itself is actually very interesting, and sharing by the speakers have brought the discussion elevated up to another level. So thank you to you all. And we also believe this short sharing session that we have today has sparked new interest among the participants, the audiences, to start venturing into this subject matter further, which of course need people of different various background and multidiscipline in making it happen. So we hope there will be some new collaborations initiated between UTM and SILK regarding this subject matter in the near future. So with that, I am ending up the session with a high appreciation to all of you who are attending this virtual meeting session this afternoon, especially to Dr. Zaino, who was in charge of all this and organized this great event. And thank you again, and have a productive day ahead to our colleagues, our friends in India, and to our friends in Malaysia. Please have a safe drive back home. Thank you very much. Bye.
Thank you. Bye-bye.
Okay. Thank you. Thanks a lot from the slide as well.
Thank you.
Thank you.